Bismillahirrahmanirrahim. I am Dr. Jamil Abbas from the Physiology Department, and this lecture is in continuation with renal physiology, and we are moving towards the next chapter that is concerned with the reabsorption. And we have studied all the details of GFR, that is number one. If you follow my cursor, the number one, this is all the process, how the things they are filtered into the proximal convoluted tubule. So we have studied all this. Now we are moving towards the proximal convoluted tubule, and the fluid which is filtered out is known as the filtrate. Now whenever I am using the word filtrate, that means the fluid which is moving in the proximal convoluted tubule and is further processed in the proximal convoluted tubule. What is meant by that processing? That means here some things are going to be reabsorbed and some things are going to be secreted. That means some of substances they are going to be reabsorbed. Here you can see the big arrow, the R, reabsorption, and some substances are going to be secreted into this one. Main important things or the main leader for this proximal convoluted tubule are concerned with the reabsorption is the sodium. Then we will move to the different glucose, amino acids, and the things which are concerned with the amino acids. Most important thing is the sodium, then the glucose, amino acids, then potassium. They are all reabsorbed from this area. Then some substances they are secreted over here. For example, uric acid, organic acid, hydrogen ion, and different types of the drugs. So let's see in detail all these things, and the whole chapter is concerned within this area, the proximal convoluted tubule. This proximal convoluted tubule has got special histological property that it has got the brush borders. These are, you can see here the written the word brush borders. They contain the brush borders. Actually these brush borders, it on the apical surfaces, and they have got proteins in them. They have got actually the carrier proteins between them, and this luminal surface area is increased by 20 times in the proximal convoluted tubule because of the presence of these brush borders or microvilli, and in the brush border, and between them you have got the carrier proteins. Then important thing is that these cells they are connected with each other and with the tight junctions, but these tight junctions are known as the so-called tight junctions or leaky tight junctions, because initially when they were discovered they were known as the tight junction. But later on, scientists came to know that although they are tight, but they are so-called tight, they can be a leaky tight junction. Because when we will move into the distal convoluted tubule, where the tight junctions are actually very tight junctions, then we have got the mitochondria in them. So surface area is increased by 20 times, and it has got the carrier proteins in them. Then tubular processing of the glomerular filtrate in the proximal tubule is when you move to this diagram, all the filtrate will move in this direction from 1 to 2 and then to loop of Henle and then to the 3, and all the filtrate is going to be processed over here. Process means some substances are going to be reabsorbed, some are the added one, and those substances or liquid or fluid which remains trapped into this nephron, it will be excreted from the body in the form of the urine. So for the urine you need filtration, you need reabsorption, you need secretion. Ultimately we are going to excrete the substances from your body. So urinary excretion is equal to the glomerular filtrate is equal to tubular reabsorption plus tubular secretion. So once you have filtered glomerular filtrate, once you filter something, then you will minus the reabsorption and you will add the secretion. That will be the urinary excretion. Then filtration and reabsorption are large quantitatively. That means I have told you earlier that you are going to filter 180 liter per day and you are passing the urine just 1.5 liter per day. That means the remaining 178.5 liter per day is going to be reabsorbed. This is the processing basically. Then small changes, very important sentences. The small change in the reabsorption will produce a large change in the urinary production. For example, 10% decrease in the reabsorption. Suppose your reabsorption in the proximal convoluted tubule or in the rest of the part of the nephron is going to be decreased by 10%. Then it will increase the urinary volume by approximately 19.6, or you can say the 20 liter per day. So you are moving from 1.5 liter to the 20 liter per day. Then the reabsorption is highly selective as compared to the filtration. We will see later on in detail all these things. Then there are two pathways which is known as the transcellular reabsorption and the paracellular reabsorption. I'm going to in detail of these in the next slide. Then there are different steps for a substance to be reabsorbed. Different steps. First of all, it has to enter from lumen to the epithelial cells of the tubule, then from epithelial cells to the interstitial tissue spaces, and then from interstitial tissue spaces to the peritubular capillary network. Let's see in detail all these things. Here is a diagram, you can well understand the things. Here is the lumen. This is the lumen of the proximal convoluted tubule, in which these are the epithelial cells, the proximal convoluted tubule, the epithelial cells. And this epithelial cell, this is the apical surface, this is the apical or luminal surface, because it is facing towards the lumen. This is known the luminal surface. And this wall, follow my cursor, this wall or this wall, this is known the basolateral surface. This is not the basolateral, this is the basolateral surface. On the basolateral surface, you will find that there is a sodium potassium pump is present over here. And this is the interstitial tissue spaces, and from where is the peritubular capillary network. So any substance which has to be reabsorbed from this area, from the lumen, they has to pass from the lumen into the epithelial cells, and then they have to enter into the interstitial tissue space over here, and then from here it will move toward the peritubular capillary network. Now the apical surface has got different types. I have told you this surface has got the brush borders. The apical surface has got the brush borders. It has got the proteins in them. It has got the increased surface area. This apical surface. The important thing present on the basolateral surface is your sodium potassium pump, which is energy required pump, and this is working for the movement of the potassium you have seen the arrow, the potassium moving in while sodium is moving out. This is the basolateral surface of this one. And these junctions, as I have told you, these are the so-called tight junctions. They are the tight leaky junctions. Actually, some substances they will move from this area, for example sodium, can move back to this lumen. Now I have told you terminology, the paracellular and the transcellular reabsorption. Reabsorption means substances are moving from this luminal surface to the cells and then into the interstitial tissues and ultimately to the peritubular capillary network. So two pathways. One is known as the transcellular. That means you can well imagine that sodium can move through this wall, luminal surface. It will enter into this area and then it will enter to this area and this area. This is the transcellular, that is passage through the cell, transcellular. And other pathway is the paracellular, that is between the cells. This pathway, if you can follow my cursor, this pathway is known as the paracellular pathway. Some substances or the solvent drag we will study later on, which is draining the urea and different substances along with that, and the chloride also. So this pathway that they are moving, the substances are moving between the two cells from this area into this area. So this is known the paracellular pathway. Now in the proximal convoluted tubule, they receive the filtrate from the Bowman capsule and pass it on to the descending limb of loop of Henle. Surface is increased because of the presence of microvilli, looks like the brush borders. Then very important few sentences. One of them is the 65% of the filtrate is reabsorbed in the proximal convoluted tubule. Then the reabsorption is isotonic. Then 65% of the sodium is reabsorbed in the PCT. Let's back to the diagram. Here you can see. So from here, or you can say from this part up to this part, or from here, this is it, from here up to this part. This is a proximal convoluted tubule. In it, reabsorption process is isotonic. That the amount of solute and solvent they are reabsorbed in equal ratio. That osmolarity of the filtrate is not going to be disturbed. The fluid moving into this area is osmolarity is not going to be disturbed because solute and solvent they are reabsorbed in the same ratio. Then 65% of the filtrate, that amount of filtrate over here, of it 65% is going to be reabsorbed from this PCT, from the proximal convoluted tubule. And the one of the very important thing that all the glucose which are filtered over here is going to be reabsorbed within this PCT. Once the filtrate has moved or joined this descending loop of lane, any glucose remains unabsorbed in the PCT will remain unabsorbed throughout the its movement into the remaining part of the nephron. It will be excreted. It will in the urine. It will be appear in the urine. So this PCT is important for the isotonic reabsorption. 65% of filtrate is big amount is reabsorbed in the proximal convoluted tubule. Then all the glucose is reabsorbed in the proximal convoluted tubule. Then it has got the brush borders which has got the proteins inside them which will assist in the reabsorption of the different substances. Then the amino acids are also very important to be reabsorbed over here. The rest of the substances we will study, bicarb we will study in detail in the chapter of the acid-base balance, and we will see later all these things. The hydrogen I will study in the next chapter of the acid-base balance. We will see the drugs later on. So this is the main property of the proximal convoluted tubule. Now, all the glucose I have told you, all the glucose up to the TM. TM means transport maximum is reabsorbed in the PCT. Transport, what is meant by the transport maximum? Let's understand with the help of an example. Suppose you are landing at the airport through a plane and you have got the 400 passenger in your plane. And outside the airport you have got 100 taxis, 100 cars which can take you to your destinations, and each car can have only seating arrangement for the 4 passengers. So that transport maximum for the coming plane is 400 passengers. This is that means actually these taxis or cars, they are nothing but the carrier proteins. These, because the transport of the sodium or the glucose mainly depend upon the, especially not the sodium, but the glucose depends upon the carrier protein. It depends upon the sodium. We will see soon all the glucose is reabsorbed. But at this stage, just understand the transport maximum. So the maximum rate at which the tubule can reabsorb a substance per minute is known as the transport maximum. That the maximum amount of the substance that can be reabsorbed per minute is known as the transport maximum of substance. Actually, this transport maximum depends upon further few things. One of the very important things is the carrier proteins. Their substance. For glucose, this is 375 milligram per deciliter. If your blood glucose level is 375 milligram per deciliter, all this can be reabsorbed. Then tight junction are so-called tight junction in the proximal PCT. Amino acids are also reabsorbed here by the pinocytosis. Secretion of the hydrogen, that hydrogen will come back into this area, and reabsorption of bicarb will occur in this proximal. I have told you all these things. Then the reabsorption of 50% of filtered urea is going to occur in the PCT. 50% of filtered urea is reabsorbed over here. Then reabsorption of chloride and potassium also going to occur in this area. At transport maximum TM, carrier system becomes saturated. Substances that are reabsorbed passively do not follow the TM. Actually, the TM is concerned with the carrier protein. Those substances will reabsorb the passive mechanism, they don't follow this TM. Their reabsorption depends upon the electrochemical gradient, permeability of the membrane for that substance, the time that fluids stay in the lumen containing that substance. Sodium follows the time gradient transport mainly. This is very important sentence. Sodium, although sodium reabsorbed in different methods in different parts of the nephron, but here sodium follows time gradient transport mainly. That means how much time it is going to stay in the lumen of the nephron, then the potential difference between the lumen and the cell. So this will cause the movement of sodium from the lumen into this cells of the nephron. Now let's see the different steps of sodium reabsorption. I have told you, first of all, we study the sodium reabsorption because sodium is the main leader concerned with the reabsorption. Now from here, from the luminal surface, sodium has to enter into the tubular cells, and from tubular cell it has to enter into the interstitial fluid, and from here it has to join the peritubular capillary network. You can see that sodium is moving from this area, then moving from here to this area, and then from here to this area. Let's see in detail all these things. Actually, if you see in the basolateral surface, you have got the sodium-potassium pump over here. This function of this pump is to push or to pump out sodium from the cells into your interstitial tissue space. So once this pump begins to function, the sodium is moved out of the interstitial tissue spaces, and the quantity of sodium in this area, if you follow my cursor, in this area is decreased. Cellular concentration of sodium is going to be decreased, and then sodium concentration decrease over here. Then the sodium can move from here to this area through different processes. We'll soon see all these processes. So simply just to understand that, first of all, your sodium potassium pump begins to its function. It will pump out sodium out of the epithelial cells, and in the epithelial cells sodium is going to be low, and this will cause movement of sodium or diffusion of sodium from this lumen into the cells. Then from here, interstitial tissue space, the sodium moves to the peritubular capillary network because of the diffusion, the process of diffusion. Let's see all these in written form. Sodium moves from the high concentration gradient, that is 140 milliequivalent in the lumen. Here you have got more and more sodium coming into the filtrate. We have got the 140 milliequivalent in the lumen to a low 12 milliequivalent inside the cell. Inside the cell it is low. Why it is low? Because function of this sodium potassium pump. Second, it has got minus 70 millivolt intracellular potential that is going to attract the sodium. This cell is it inside the cell. You know the resting membrane potential is minus 70 millivolt. Intracellular, we have got less sodium over here, and it will attract the sodium. Then we have got different glucose transporters present on this, although they are not shown this, but we are going to see in the next slide, which is known as the sodium glucose transporter 2, SGL2. Sodium glucose transporter 2 in the early part of the nephron. Actually, the proximal convoluted tubule is divided into the two parts, mainly the first part and the second part, and some physiology divided into three parts. But mainly the first part contains sodium glucose transporters, which are known as transporters 2 in the early part, and 90% of the filtered glucose and remaining 10% is by the, actually in the early part where the sodium glucose sodium along with the glucose, that is glucose is going to, we will see later on how the glucose is reabsorbed. Sodium and glucose, they both of them, they are going to be reabsorbed in the same way. So the earlier part, that the first part, reabsorbs 90% of the filtered glucose, remaining 10% reabsorbed in the sodium glucose transporter 1. This is present on the last part of the nephron, last part of the PCT, sodium glucose transporter 1. And on the basolateral surface, on this surface, although it's not shown over here, we'll move to the next slide. We have got the sodium glucose transporter 2. It's only, this is written twice, this is only sodium glucose transporter 2 which are present. They will carry the glucose to the interstitium. They will move to the interstitium, glucose transporters 2. Here you can see the diagram, the theoretical diagram. That is the, we have next, here you can see sodium glucose transporter 2 and sodium glucose transporter 1 present on the initial and the later part of the proximal convoluted tubule. Here you have got initial part, we have got sodium glucose transporter 2, which are going to reabsorb 90% of the glucose. And here we have divided S1 and S2 segments of the proximal tubule. We divide the segments into two parts. And then later on we have got, in the last part of the PCT, we have got the sodium glucose transporter 1, which is going to reabsorb your 10% of the glucose. We will see later on why I am using the word glucose and sodium simultaneously, because they are going to be reabsorbed simultaneously. Here you can see we are not concerned with the intestine, we are concerned with this part of the nephron. We are concerned with the kidney, which is concerned with this diagram actually for the sodium and the glucose reabsorption. You can see this is a luminal surface. This is the luminal surface in which we have got the carrier protein, which is known sodium glucose transporter 2 in the initial part, and sodium and glucose were going to be reabsorbed simultaneously. From here the sodium will move into the interstitial tissue space, and on the inside, you have got the GLUT2, you have got the glucose transporter 2 on other surface, and you have the glucose transporter 1. So these are the different name of the transporters which are present in different parts of the nephron. In the initial part we have got mainly the sodium glucose transporter 2, and other side we have got the GLUT2 only, and on here you have got the GLUT1. Now, first choice, whenever the glucose is going to be reabsorbed, here is a purple color. This is your carrier protein shown over here, and this is the filtrate coming down. This is the tubular epithelial cell, and these are the so-called tight junction between them, and these are interstitial tissue spaces, and we have got the peritubular capillary network. So the carrier protein, once this sodium potassium pump begins to function, it will move 3 sodium out of the cell, the 3 sodium moving here. So that's why sodium concentration is going to decrease over here. Once the sodium concentration decreases over here, that will cause the movement of the sodium through its carrier protein from the lumen into the cell. This carrier protein has got two sides of the attachment. On one side there is attachment of sodium, on the other side the glucose is going to be attached, and the sodium and the glucose, they are going to be reabsorbed simultaneously. Along, that means glucose is going to be reabsorbed along with the sodium and enters into this epithelial cells, and from here the sodium will move into the interstitial tissue space through the working of this sodium potassium pump. Then on the other side you will see the two potassium, they are moving into the cell. So that means this cell is going to be accumulated more and more potassium, but God has provided a very good mechanism, that is potassium which are accumulating inside cell, they are not going to be retained in the cell. They have got the potassium leak channels over here. So the potassium which is moving over here, it will move back into the interstitial tissue space through their leak channel. So it again is going to be reabsorbed from this area and will move back to this area. Some of the potassium is going to be reabsorbed into the peritubular capillary network. So this is your carrier protein, and this is your sodium potassium pump, and this is your ionic channels. This is your paracellular pathway, and this is your this chloride is using the paracellular between the cells, and this is your transcellular pathway. And then glucose is reabsorbed through the sodium. This is your primary active transport. This is which is using the energy, primary active transport. This is dark reddish arrow for the sodium, primary active transport. And this bluish arrow is the passive diffusion. This is a passive diffusion. And this is also known as secondary active transport. The glucose is the secondary actively transport. You have seen all these things in the chapter of the cell physiology. Now, different steps of sodium reabsorption I have told you earlier, but here you have got the written form. Sodium reabsorption, the PCT, don't follow the TM maximum, transport maximum system. It follows gradient time transport principle. Sodium potassium pump on the basolateral surface of the tubular epithelium push the sodium from epithelial cells. This is abbreviation for the epithelial cells to interstitial tissue space. Again, this is the abbreviation for the interstitial tissue space. Sodium potassium pump empties the epithelial cells and create less sodium quantitatively in the epithelial cell. Efficacy of the sodium potassium pump is far greater than the actual sodium reabsorption. It's a very important point to be noted, that sodium potassium pump can remove more sodium than is required. Then from interstitial tissue space, some of its sodium will enter in the PCT, peritubular capillary network, and some will leak back to the lumen through so-called tight junctions. Back to the diagram. That once the sodium is going to be reabsorbed and it is moving into the interstitial tissue, I am saying that some of the sodium will move into this direction, and some, although it's not shown over here, but follow my cursor, some of the sodium will move through this so-called tight junction back to this lumen. Some of the sodium will be reabsorbed in it. So once the sodium enters into the interstitial tissue space, it has got two pathways. Some of it is going to be enter into the peritubular capillary network, and some of it is going to back through the so-called junction into the this lumen. And this sodium is going to follow the time gradient phenomena, that how much time it is going to stay in the lumen, and then how much concentration gradient is present over here. Now from luminal surface, sodium enters the epithelial cell through a carrier protein along with the glucose, and the first choice for the glucose, first choice for the sodium to reabsorb glucose, then the amino acids, and then the chloride may be there. Then from interstitial tissue space to the peritubular capillary network, Sodium, water, and other substances are reabsorbed from interstitial tissue space to the PCT by ultrafiltration, a passive process, driven by the hydrostatic and the colloidal osmotic pressure gradient. We will see later on all these things. Here, reabsorption is because of the pressure difference of 10 millimeter of the mercury. If you remember that we have seen in the earlier lecture that the filtration is because of the pressure difference of 10. Here you can see the reabsorption is also because of the pressure difference of the 10. This reabsorption 10 net forces that actually what's happened in the interstitial tissue space, in the peritubular capillary network, we have got more proteins, we have got more oncotic pressure over here, and this more oncotic pressure is because reason is that proteins, they are albumin, they are not going to be filtered out, so they are moving into the capillaries and they will attract the different substances into the peritubular capillary network. Here you have got the big arrow. Soon we will see in detail all these forces. Here is the diagram for the brush borders and how the sodium is moving, and you will see that this is the carrier protein through, and this is the brush borders. This is the carrier protein present between them, and this reabsorption of sodium along with the glucose occurring over here. Reabsorption of sodium along with the chloride. Reabsorption of sodium along with the different vitamins. The reabsorption of sodium, although not shown over here, the reabsorption along with amino acids also occurring in the same way. Then on this other surface you will find that there is sodium potassium pump, which is pumping the sodium here, and some of the sodium will be entered into this area and some will move back to that area. Then we will move from here up till now. We will see in the next lecture how the glucose is going to be reabsorbed. Thank you very much.